recording. Okay. All right. What was the question?
I'm just trying to see, did you post a project against the C or the Python code? Because when I looked on Blackboard, it was just like a sample of code. That was it. I didn't see it in project on it. Or I'm tripping.
You're tripping. It was in the description. I didn't write a PDF. I just typed it in the.
Oh, maybe.
Yeah.
I just
read the thing. Yeah. Yeah. I typed it into the little assignment thing. Yeah. Yeah. I didn't make like a separate PDF or anything. Okay. Are there any questions about that? The project is due on Friday. What's up?
So regarding, so I've got most of it done because I was able to get it to work with the example and like you hard coded in the one test case.
Yeah.
Example. But when I tried using like in-class example or homework example, it didn't work properly
Ah.
because the way I figured I would do it is because you have your X event list and your H event list. I
Okay.
figured out when you find an X event list based on if it's in the first half, it would be a negative number. If it's on the second half, it'd be a positive number. Based on that, you would use your shift like if it's a negative or positive X value, where it is like on the number line.
Okay. I mean that makes sense. You're talking about where you shift it to do the
Yeah, because
stuff?
the first index of an array would be 0.
Yeah.
But on the number line, it'd be -5. So it's just figuring out the shift.
Yeah, so you got to figure out like where. Oh, that's gonna be tricky. So you're gonna try to infer with the.
That's what I did. And I got it to work with the one example,
Yeah.
but I couldn't get to work with the example. So I
Yeah.
can get in office hours.
Yeah, like bring it to me in office hours today. I'd like to look at it, but yeah, that's trying to infer the like in position in the number, like in the sequence. That's gonna be tough. It's much easier just to like walk around, but that's pretty cool. I want to see how you implemented that. You said you got it working for.
I got it working for the like the one example you had hard coded in.
Okay.
But I tried it with the one in class example, an easy one, and it kind of worked. Like if it's 0, that always worked, and I think if it was negative, like it was negative would work. But I think my positive convolutions were messed up a little bit.
Yeah, I think you might be
Yeah.
maybe trying too hard. That's
Probably.
tricky, but yeah, but come to office hours. I want to see that. That sounds pretty cool. Any other questions about that assignment? All right. In that case, let's get going. So, today's lecture is called The Homogeneous Response. The chapter in the textbook said nth order, linear, constant, coefficient, difference equations, which is what we're going to talk about. But I've learned preparing these lectures from reading the textbook, usually the textbook like chapter name is like about something, and then like what the chapter is actually about is something totally different. So, let's see here. Let's start off with what we know. We know how to model a discrete time system. Right? We know that we're going to have some input x of n, go into some box that's got some transfer function that's going to output to some y of n, right? And we know that we can write that as an expression or a mathematical equation, say that y n is equal to the transfer function acting upon our input sequence, which now we know to model as simply x of n convolved with h of n, right? Everyone good up to that point? If not, we need to talk because you're a little behind the curve. So here's the question that we're going to ask today and over the next couple of lectures, which is h of n, the impulse response. What if we don't know what h of n is? right? Everything we've done so far is sort of gone with, well, here's h of n, what's y of n going to be? Or like, can we mess around with h of n? But what if we don't know what it is, right? All right, this technique is not going to work. And so the question we want to ask is, can we use blue? Can we figure out h of n by providing values of x of n and observing the resulting y of n? So simply put, can we take an empty black box, can we spit input sequences into it, look at what the output sequences are, and use that to figure out what the impulse response is? And the answer to that question, of course, is yes. Yes, we sure can. But how? So in this class, there's a bunch of different responses. But in this class, we're going to really care about three classes, or three types of responses. So I'm just going to say we'll consider three types of response. The first one is called the homogeneous response, or homogeneous response. This, of course, is today's topic. The second one is called the impulse response. Right, this is what we really want, because that tells us everything else. And the third one is called the step response. And we'll just say this one is still kind of useful. Okay, so we're going to try to derive by just simply looking at the input sequences and the output sequences. We're going to try to figure out these three types of responses, right? And between these three, we'll know kind of everything we need to know, everything we care to know about that particular system. So and today we're going to talk about the homogeneous response. Now before we can do that, we need to introduce the sort of concept that was the title of the chapter. So let's just say this first. Let's introduce this monster. Nth order linear constant coefficient difference equation. Good Lord. Okay. Now, when we say difference equation in this class, a difference equation in discrete time is approximately the same thing as a differential equation in continuous time. So when we say difference equation in your linear system class, it's a differential equation. You guys have all taken DiffQ 1 and 2? Cool. All right. So similar stuff, but not quite the same thing. All right. So first, let's just look at the basic form of this equation. And that is this. On the left-hand side, we'll have a sum, k equals 0 to n, a of k times y to the n minus k, and that's equal to a sum m equals 0. The little m is equal to 0, and big M of b sub m times x of n minus m. So that's our basic form, and we get the sort of stuff from its name from all of this, right? So that's nth order, whatever that n is. We have a and k and b of k. Those are our constant coefficients. And the equation, of course, is linear, which has a more sophisticated definition, but for us, it has no exponents or logarithms or anything weird, right? It's just stuff multiplied by other stuff. Nothing is raised to the second power or anything like that. So that's the form of the equation. Are there any questions about the structure? The notation's kind of hairy, but there's really not much going on there. And hopefully we'll see from this example that we're about to do, this can actually be distilled down to something that's really quite simple. So, all right, make sure we're good over there. So let's do an example of taking something that we've seen before and representing it in this form. So let's see, what I want to say here is represent the accumulator system as a linear constant coefficient difference equation. And remember the expression that we had for the accumulator, it's just the one that adds everything up, right? So y is equal to the sum, k is equal to negative infinity and goes to n of just x of k, right? This is the one that starts at negative infinity. Wherever n we're at, we just add them all up until we get to that n, and then we keep going, right? Every subsequent y of n is just the sum of all the previous ones. Yeah? Okay, so we got to do a little bit of algebra to get it from this into that form that we need. So the first step we want to do is this. We want to isolate the last term. So what we're going to do here is we're going to say that y of n is equal to x of n plus, what do we think is going to follow the plus? If I've taken that guy and stripped out x of n, what am I left with? Say it again. It's not k.
The summation up to n minus 1.
What's that?
The summation up to n minus 1.
Yeah, right. So we took out the last one. All right, all we have left is all of the other ones, right? So what's going to be left is same deal. Sum k negative infinity, but this time it's n minus 1 of x of k, right? Does that kind of make sense? See what we've done there? Now, we can also note that what is y of n minus 1 going to be equal to? The output term that came right before the last output term. What's it equal to?
Just the second part of the previous line.
You are absolutely right, man. Yeah. So y of n minus 1 is equal to this guy, right? The summation of k equals negative infinity to n minus 1 of x of k. Are there any questions about those two steps? That's the most important part, right? If you understand that, everything else is going to be easy. But if you don't understand that, everything else is going to be really hard. Right? All we did was take out x of n, and we're left with everything that was left over, so everything up to n minus 1. We also noted that y of n minus 1 is going to be equal to the summation of everything up to n minus 1. Right? It should make kind of an intuitive sense if you stop and sort of think about it a little bit. So we can rewrite our initial expression here. So I'm going to say this, as y of n now, right, coming from this expression, y of n is equal to x of n plus this thing that we now determine is equal to y of n minus 1. Y of n is equal to x of n plus y of n minus 1. Cool. All right. Now we just do a little bit of algebra to shift it around. As we know, the y is on the one side, all the x is on the other side. So what we're going to say is that we have x y of n minus y of n minus 1 is equal to x of n. Right? And that's what we wanted. This is our nth order linear constant coefficient difference equation. This one right here. And if we go back and feed it back to that form, it kind of makes sense, right? Let me do it in blue. Let me do it in green. That'd be fun. So we have the sum as k goes to 0. What is our capital N in this case? What is the order of this difference equation? It's not n. N has to have a number now. So that's our general form. We distilled it down to that. So, what's big N? You guys are way overthinking it, man. Let it be easy, man. This stuff is easy. Just let it be easy. Yeah, 2, right? Yeah, because we had y of n, then we had y of n minus 1. So n is, well, it's not 2, I should say. It happens twice. But remember, where do we start? Start at 0. So it's going to be in actuality 1. Did you say 1 the first time?
I said first.
Oh, okay. Were you right for the right reasons?
No.
Oh, okay. Then never mind. I don't feel bad.
Just because I looked at it, it was like, I don't think it is.
Is it 1? Yeah, it is 1, right? Because we have y of n, and then n minus 1 means we're going to go 0, then 1. Yeah.
I thought you said no, I was thinking 2.
What's that?
I thought you said nothing else. Oh, then it's trying to be
Oh, that was my mistake. My bad, guys. Okay. So a of k times y of n minus k is equal to little m equals 0. In this case, what's our big N? Equal to 0. Good. Yeah. B of k times x of n minus, or excuse me, not b of k, b of m times x of n minus m. Okay. And then what is, not quite done yet, because now we have to have our values for a of k, right? A of k only has 2 values. What are they? Or a only has 2 values. What are they? Not 0 and 1. look at what we got. This is important, right? As undergrad students, we always like sort of get freaked out by weird notation, right? Sigmas and stuff like that. But you got to remember that it's really, there's nothing to it. So if this is our equation, all we're doing is taking that expression, we're representing it this way, right? We've already figured out this is k equals 0, and that's k equals 1, right? And that's m equals 0. And there is nothing past 0, there is nothing past 1 for k. So what gets multiplied by our y term when k is equal to 0? We've come to that. No eye contact, please. What's that?
It's not in.
N. Where did you get N from, man? What is being multiplied by y?
1.
Thank you, it's 1. Yeah, so it's 1. It's just 1. Right? Everybody sees that. It's 1, right? If there's nothing there, that's 1, right? Now, when k is equal to 1, what is y being multiplied by? By negative 1, right? Because we have minus y of n minus 1. Yeah, groovy. What about x of n? When m is equal to 0, what is b of n? What's b of 0? It's 1, right? Good. That's all there is to it. See what I mean? It's easy. Just let it be easy. Don't overthink it. Don't get weird. What is multiplied by y? It's just 1. So yeah, a of k is got a 1 and a negative 1. And b of m is just 1. That's all there is to it. So there we go. That's the end of the problem.
So we're just solving for A of K and B of M?
We're not solving for anything. We're just,
Oh, just
yeah. We're just looking. We're just looking at a of k and b of k or b of m and seeing what they are. That's the beauty of it. We don't even have to we don't have to do any algebra. We don't have to think about it. We just look at it and be like, oh yeah, it's 1, it's negative 1, and it's 1 again. Anyone who tells you it's more complicated than that is lying to you. All right, so any questions about that? Hold on, somebody asked, can you explain that again for the Discord? Yeah, so all we were doing, folks on the Discord, is we're just representing that expression in general terms down here, right? Since we have y of n, this first one, well, that's our k equals 0. And the second term is our k equals 1. On the x side, we have m equals 0. So here we can see on the y side that k just goes from 0 to 1. So that's why we have k equals 0, and it stops at 1. And for the constants, a of k, we just have to look and see, well, what is being multiplied, right? And when k equals 0, y of n is clearly being multiplied by 1. And when k is equal to 1, because it's minus k, remember we have a summation, so everything should be plus. So for minusing, or for subtracting, that means we have a negative coefficient. So here we can see that when k is equal to 1, we're multiplying y by negative 1. So that's why we have a negative 1 sitting there. And the same thing on the flip side. When m is equal to 0, we can see that x of n is being multiplied by 1. So b of m is just equal to 1. Cool? Right on. Okay. So one last thing before we, yeah, we got time. We're good. Okay. Before we move on, is we can represent these things graphically. We can make a flow chart. And the flow chart for this system is going to look something like this. As per usual, we'll have x of n, and then that will move over. All right, close enough. All right, that'll feed into some summation thing. That gives y of n. And then all we're doing, notice here that we just have, oh, did I make a mistake somewhere? Let's see. No, we're fine. Okay. Right. Y of n minus y of n minus 1. If we come back up here, right, y of n is equal to x of n plus y of n minus 1. So that means down here, all we're going to do is take and create one of those delay systems, right, where n of d is equal to 1. And then have it feed back around. So that on the outside here we have, this one is y of n minus 1, right? In this delay system, let's take a little aside, what's the transfer function here equal to for a delay system?
Direct delta of n minus n.
What's that?
Is it direct delta of n minus n?
You are absolutely right. Delta of n, except this time we've defined nd, right?
Oh, the 1.
Yeah. This right here, taking the summation, passing it out, doing the delay sequence by convolving with h of n of delta n equals 1, or n minus 1, this is at the top of my list for next week's Python project, is implementing this right here. Because that's a little bit of everything that we talked about so far. Okay, so that's how we represent these things graphically. A lot of times it's going to come down to just stuff being sort of pushed around and multiplied by y's and x's, and maybe some constants thrown there on the end. So, any questions about how we do this graphically? Okay, cool. Now let's get on to the good part. Now that we've talked about that linear constant coefficient equation, we can actually talk about the homogeneous response. Okay. So let's see. We've got a box. And we don't know what's in it. We're going to give it some x of n. We're going to get out some y of n. Now the one we've probably heard about is the impulse response, right? In fact, we've already talked about the impulse response. What is, well, never mind. I don't want to go there yet. I was going to say, well, how do we figure out what the impulse response is? Well, does anyone know how we figure out the impulse response? We're going to get this in linear systems?
Fourier.
What's that?
Fourier?
Fourier transform comes into the math. We're going to do that on Friday. But in simple terms, what do you get? We notice the output, but what is the input? Yeah, after you slap it with an impulse function, you see what happens, right? That's the impulse response. You feed it one impulse sequence, and the output is whatever that's the impulse response, right? That's why we love the impulse response, because it's really easy to see what the result is, right? This works in 2 dimensions as well. One of my favorite stories is, you guys know, you've heard of the Hubble telescope, right? They launched it, and they found out the mirror, when they put it in space, was deformed by a little bit. Yeah, so it was actually kind of warped in such a way. But they figured out, well, we could, if we knew what the impulse response of the mirror was, then we could code in a little bit of a thing to correct the deformation in the mirror, right, in 2 dimensions. So if for a photograph, what would be the impulse response? Like, what would be an example of an impulse function in 2 dimensions?
The amount of pixels.
What's that?
Like the amount of pixels.
Yeah, but what would it look like, though?
So,
Right, we know in, and I'm talking right, in 1 dimension, the impulse response is 0s and then 1 tall signal, right? Well, in 2 dimensions, what's that going to look like? You guys taken, if you haven't, Swarov's pattern recognition class, or image processing class is awesome. So in 2 dimensions, what's this going to look like?
A
black and white photo?
Yeah, well, not black and white, because it's still an impulse response, right?
He had to do something in his intro class with a black and white photo, and you had to input a message within it
That's pretty cool.
and then decrypt it.
That's real cool. Yeah. So we're getting kind of off track here, but that's the gist, right? So the impulse response for if you want to give an impulse response to a camera, find out an image system's impulse response. Well, you feed a thing, it's a whole bunch of zeros and then a one right in the middle. Yeah. How do you think they did this for the Hubble telescope? The answer is really cool. Any guesses?
They did that everywhere there was a voltage.
What's that?
They just did that wherever it worked.
No,
Like,
no, because you got to take the whole thing. But you got to. How would you telescopes in space? You got to get a thing to figure out what its impulse response is. What do? What do you take a picture of?
Here.
Not the Earth. The Earth doesn't look like that. Not the sun. But you're close. You're on the right track. Not the moon. You're getting closer. Well, not really, but. Take a picture of a star. Take a picture of a single. They found a place where they could take one photo of a single star in the middle of a black field, and from that they were able to calculate the impulse response of the mirror and do the autocorrection. I think it's amazing. I think that's absolutely fascinating. Edward is correct. Yeah. Okay. So all of that to say, that was a messy tangent, but all of that to say is the impulse response is, well, we're going to feed an impulse and we're going to see what happens. The homogeneous response is, let's just give it zeros. What if we give it nothing? The homogeneous response is, let's just give it a sequence that consists entirely of zeros and see what we get out. So let me write that down. So that is the response observed all right, speed up. Observed at y of n for an input sequence x of n equals 0 for all values of n. Right. So what we'll say is x sub h for homogeneous of n is equal to 0 for negative infinity is less than n is less than positive infinity. We want to know what is y sub h of n. So if we give it zeros, what do we get out? Well, let's figure it out. So let's go ahead and start with our difference equation. I'm going to jot that down. All right, the summation, k equals 0 to n. We're going to say it a whole bunch of times so it sticks in your brain. A of k times y, n minus k is equal to the summation of m equals 0 to big M, b of m x n minus m. Now, if we're going to write that looking for our homogeneous thing, what is the x side here? What is that going to be? Let's take a step back. What is the homogeneous response?
What happens if we put nothing but zeros?
If we put nothing but zeros. So, what happens to the side of the equation that's got all the x's if we're looking for the homogeneous response?
It's just all zeros.
It's a 0, right? So that's going to be that is equal to 0. So we can simplify it a little bit to say that the right-hand side here is going to be largely the same. K equals 0 to n a of k times y sub h of n minus k is equal to 0. Okay, here is what I lovingly refer to as the important part. I.e. the part that's on your homework and the part that'll be on your test. The solution to this y sub hn takes the form y sub hn is equal to, that's gross, the summation from, what I'm going to say, little m equals 1 to big N of a of m times z of m raised to the nth power. And now for the first time in this course we see z rear its ugly head. It's a whole segment of this course that's devoted to the weird things that we can do with z. Okay, so it takes that form. One thing to note, a of m is an arbitrary constant. Right? For the purposes of this course, for now, we are not going to care what a is. Right? It's just a constant. Who cares? But we do care about figuring out what z of m is. Z of m is the root of the polynomial a, which is a function of z. Whoa, that was cool. A is a function of z is equal to, again, the summation k equals 0 to big N of a of k times z to the a of k. So when I say polynomial, I mean it in exactly the same way as it was meant in your high school Algebra 1 class. So, a couple of things to note about this guy. First thing that we should note is that that is the same n as the beginning. From the equation. And the a of k's are going to be the same constants as our equation. So I don't need to guess what they are, but will be given to us, so to speak. All right. So all I have to say is y sub h is equal to the summation m equals little 1 to big M, or little m equals 1 to big N of a of m, which is an arbitrary constant, times z of m raised to the nth power. And those z of m's are the roots of the polynomial. A z is equal to the summation from 0 to n of a k times z to the minus k. So that was a lot. Let's do an example. An example. Here's an example problem. Determine the homogeneous response of the system. Almost done. Represented by the following difference equation. Y of n minus, not plus, minus 5y then minus 1 plus 6y n minus 2 is equal to 2x of n minus 1. So this is our nth order linear constant coefficient difference equation. We need to find the homogeneous response. We'll also use the same equation later on to find the impulse and step response. But for now, we're going to find the homogeneous response. So we're going to set that right-hand side equal to 0. But first what we need to do is answer a few questions. What is in, or I should have said what are in grammar and A of k. So, and remember, these can be figured out simply by inspection, not by doing any weird calculations. What is in this case? Good, it's 2. I see Hunter also got it. Yeah, it equals 2, right? It's the count the number of times the y appears and subtract 1, right? All right. Which means that we're going to have, tablet is struggling, an a of 0, an a of 1, and an a of 2. What is a of 0 equal to? Or a sub 0? Hunter says 1. You're absolutely correct. A of 0 is equal to 1. How about a sub 1? Hunter says it's equal to 5. Yep, it's equal to 5. And finally, a sub 2 is going to be what? What do you guess? 6. Positive 6, right? Any questions about how we derived in or our constants, a0, a1, a2? Oh, you're right. It's minus 5 for a sub 1. Good catch. It was minus 5y in minus 1. All right, so from there, we got to go kind of fast. Our next stop is that we're looking for y sub h of n is equal to the summation of k equals 0. Now we're going to 2 of a of k times a of capital M. Mess this all up. M equals 0. A of M times z of M to the negative k. Where we know that z is going to be the roots of this polynomial. A of z equals summation k equals 0 to 2 of a of k times z to the negative k. So if we expand that out, then we'll have, we go 0, 1, 2, so that'll be a 0 times z to the negative 0 plus a 1 times z to the negative 1 plus a 2 times z to the negative 2. Z to the negative 0 is just 1, right? So we know we're going to have a 0 plus a 1 times z to the negative 1 plus a2 times z to the negative 2. And then finally we plug in our values here and we have that a of z, our polynomial here, is 1 minus 5z to the negative 1 plus 6 z to the negative 2. And we remember from our high school algebra class, the roots are found by setting AZ equal to 0 and solving for Z, right? So we'll have this 1 minus, I'm going to rearrange this, 5 over Z plus 6 over Z squared is equal to 0. Now it's just algebra class, solving for Z. The easiest way to set this up is to, let's multiply Z squared to both sides. So that's going to be 1, or Z squared times all of this is equal to Z squared times 0, which is going to get us Z squared minus 5Z plus 6 is equal to 0. We do a little bit of factoring, and that's going to be Z minus 3 and Z minus 2 is equal to 0, which means that we have roots at Z equals 3 and Z equals 2. Therefore, the homogeneous response y sub h of n is equal to a of 1 times 2 to the n plus a2 times 3 to the n. And that's our final answer for the homogeneous response. Now, one last thing before I let you guys go that I want to note is, let's do this. Note, since A of m is arbitrary, the order doesn't matter, which we could have said y of h of n is equal to a1 times 3 to the n plus a2 times 2 to the n. That is, go away, still an acceptable answer. So that means that for the homework and the tests, the order in which you put them in doesn't matter. It's all going to be correct. So that is how we calculate the homogeneous response. We take our function that we're given, or our difference equation that we start with, we figure out what is in, we figure out what are our constants for a sub k, and once we have that, we plug them in to our polynomial, solve for z, those are our roots, homogeneous response is a function of those roots. Any questions about that? All right, no more questions. Thank you so much, guys. Like I said, your homework assignment that's going to be due on Friday is like 4 problems that are just like this. You give in the difference equation, give in the homogeneous response. So it should take you shouldn't take you more than 10 minutes to do if you understood what we talked about today. All right? All right, thanks, guys. I'll see you on Friday.
Difference between image processing and then digital system.
Brown, what's your question?
There was the signal processing. There was digital signal processing and then image processing. When I was looking at the syllabus for both that Tech has, they look very similar.
Except digital signal processing is one. They are similar in that they're both. There's a lot of overlap. They're going to talk about a lot of the same stuff. Digital signal processing is in 1 dimension. Image processing is 2 dimensions. That's honestly that's the fundamental difference.
Oh, okay. I was wondering because I looked at it and I was like, they look the same because it's